let's see what happens. And remember the last time, something very basic about stability of floating bodies, but it's very important that you really have that inside your head. And I made a new drawing because what I kind of copied from Wikipedia was maybe not all that good. My pointer. So the question is, if you have a body that's floating on water, like here, and then the question is this floating body stable or not? Then you have the buoyancy force, which is in the center of the displaced water, right? And then the body itself has a center of gravity called G. And the question is, if you give that a rotation called d phi, a small rotation, this can also be done for large rotations, no problem about that. But we are looking only at small rotation theory. And then what you'll see that, you dip this side deeper into the water, right? And this side you lift up with the water when you rotate it. And that means a pressure difference. When this dips down, you increase the pressure on this side, right? And that gives you a contribution to a what we call an uprighting moment, kind of a correction moment. And that is the integration of the water line area of the increase of pressure, and of course the moment arm and the area dA. So integrate that over the water plane area, right? And the pressure is rho g times x d phi. That's how far it goes into the water, x times d phi, right? And then the moment arm x, so that gives us rho g I, where I is the second area moment of the water plane area. Okay, so that it is a very logical calculation of this moment contribution. And of course, you have the buoyancy force equal to the gravity force, which is the density of water, acceleration of gravity, and the displaced volume. And then we can say that the fact that we're getting this correction moment, right? That corresponds to moving the buoyancy force. Similarly, if we take the buoyancy force and we take the distance from B to some unknown point M, where the corrected buoyancy force will go through, that's Bm times d phi, and the force Fb gives that moment contribution. So Bm is kind of a derived quantity from the uprighting moment. You see? So it's in one way it's kind of a mysterious quantity when we talk about Bm and Gm, but it's really a metric expression of the uprighting moment. Okay, so the system really isn't in balance when it's rotating. It wants to get back. So in reality, you have to force a moment on the structure in order to make it rotate. And if you look at large rotation theory, and let's say you have a ship, and then you also can look at a rotation of the ship by an angle phi, right? And you can look at the uprighting moment as a function of phi here. So you start with a quantity here. And then we are talking about the well, I should say, yeah, it's really well, the moment force starts really here. Of course, the moment as such starts at 0, and then it will normally go up, but it can also go down, right? But if it's negative, of course, then it is unstable. But the function can go something like this if we have very large rotations. That means if you take a boat and you tip it over, you use larger and larger force, but then you come to a point where it actually will just tilt around and then bottoms up. So GM is a concept for stability, and the higher value of the GM, the stiffer the ship is against rotations. And we touched upon another quantity too when we look at very large floating structures. There is, of course, the interaction between the structure and the water. And when you dip further into the water, it's similar to the dP as we talked about earlier as a function of how far you dip it into water. When you rotate it, here you look at the displacement, and so the water is like a spring, right? And the spring constant is called Kc, and in this case it is Newton per square meter, because it's Kc is the force Newton per meter square, and that is simply the spring constant. The force is Newton per meter, is Kc times meter. So, this is the force per length of the beam. And the spring constant is simply it is rho water times G times the width of the beam. So we can call that B, for instance. But anyway, if you can solve this problem as an analytical problem with differential equation, and you'll find that if you apply a force, it will bend, and then you'll have an inflection point where it goes from a positive bending moment to a negative bending moment, and that inflection point is what is called the characteristic length. And it's not really correct in this drawing, because the inflection point, where the moment is changing sign, is not out there. It's somewhere here. But the thing is, if you have a very stiff beam, and that is the bending stiffness of the beam, you'll have a very large characteristic length. The length says something about the stiffness and how this long floating beam will bend, right? So if we look here now, if the length of the structure compared with the wavelength we have here. So you see, if the length is of the structure is small compared to the wavelength, of course it will move like a rigid body. But if the body is very, very long in relation to the wavelength, we won't have any overall rotations of the body, or not even a heave moment if we have very long structure in relation to the wavelength. Understand that? But if the structure is very flexible, then of course it will start bending for even a wavelength that is of the same order as the body. So, for instance, a ship, will typically bend when you have wavelengths that are of the same order as the ship itself. It is flexible. And if you have a very, very long structure, which also is very flexible, then you have this kind of deformations. And typically, if you are talking about a floating airport, then you'll have this kind of situation where with a very large floating structure which has a flexibility in relation to very large waves. So that you have to account for. So you have to think about this this problem so you understand it. So if you're talking about an airport, very large floating structure, lambda divided by the total length of the structure is in order 1 to 50, 1 to 100. That's a typical stiffness characteristics. And then you see in relation to the wavelength, you will have some elastic deformations of a structure like that, but not rigid body motions, right? The whole structure won't heave at the same time, but you'll have, of course, deformations due to the waves, and you have forces. So you have to design for these forces, even though the whole structure is not moving as a rigid body, because it's so large. So, how do we deal with these forces? And for, let's say, a floating city or a floating airport, these forces will be very large. Well, you can divide up the waterline area in subregions. You can reduce the water plane area by a semi-sub type of structural design. You know what we mean by that? We have a submerged body that gives buoyancy, and then there are columns that go through the water plane, reducing the water plane area. So the forces in that wave zone will be smaller than if you had a continuous body. And one can also use something like an air cushion principle. We'll look at that too. What does that mean? And here in this figure, you see a prismatic, a box-like structure, right? And you have waves coming in here from this side. And you see these waves bend around the structure, and the wave pattern is changed, and you get these forces on the structure. What you would like to do is not to change the wave pattern in such a way that you get very large forces. And here you see one idea for reducing these pressure forces that you get under this big box. The waves are associated with pressure. Of course, it has to do with the wave height, but in this zone where the structure is, of course you don't have a free surface, but you still have pressure variations under the floating body. That's like the same in a ship. You don't have a free surface as such under the ship, but you have large variations in water pressure which are associated with the waves going by the ship. So the idea is that if you make a box here which is filled with air inside, what you'll see is that these waves, they continue inside. Understand what I'm saying? We have a structure which is a box, the water here, and then we either have some pressurized air, or we have some pressurized air. So the water plane inside is like this, right? So that air pressure carries the structure. And if we have a wave coming here, it will continue inside like that. And of course, the good thing with the air is that the air pressure will be the same everywhere here. Understand? Unlike water, which has a lot of inertia and therefore gives you different pressures, the air has very little inertia. So even though these waves go up and down here, they don't give any pressure distribution on this bottom. Right? It sounds very good. But what you should do when you come home, so to speak, is to take, you fill your wash basin with water. Oops. Not necessarily any waves. And then you take a glass like this, and that will go down, and the weight of the glass will, pressure the air down. You have some compression of the air, right? Do you think that is stable? No. It's very, very unstable. But because in fact, the water plane area in this case is just the thickness of the glass. Right? So you have very little restoring uprighting moment in a situation like this. And of course, also if this is a glass or a cup of some sort, the center of gravity will be up there. So there's no stability of a system like that. So that's the bad news. The good news that we started with was that you get very small pressure differences in the structure, but because the waves more or less just go through here. But then there's an example where you divide this space inside into 4 different chambers. So if you see this from above and we divide it like this, and the waves come in here, then this will be more stable because you have 4 air chambers instead of just 1. And the last situation is that you have a double wall structure, right? And that double wall is sufficient to provide stability. But at the same time, we have these waves that can go through here without imposing extra forces on the structure. So that is okay, the last one. But of course, then you are somewhere in between that situation and that situation. Right? You get some more forces on the structure because this part will draw upon it some extra forces. So this air chamber cushion floater is kind of a mixed idea, I would say. And of course, if you more or less lose the air pressure, if you have a hole inside, then of course the air would like to get out because it's pressurized. It would like to be atmospheric, and then the structure will sink in. So, from safety point of view, that is questionable. But here you see the situation: a box and one chamber, but unstable. A box and 4 chambers, a little bit more stable. And then you have this surrounding double wall. And one can compute the moments for these different cases and see what it implies. But certainly, if you are going to analyze a big floating structure, you have to do the hydrodynamics and the wave loading very seriously. So this is an illustration. If you have several chambers, it's more stable than having only one chamber. So airports that are floating offshore, that is still more or less a dream. You remember that the Japanese have built a floating airport in scale, let's say 1 to 5, 1,000-meter long airport, and done some experiences with that, but still have not taken the step to a full-scale floating airport. You have the airport in Osaka, but it's a landfill. It's not floating. So it's out at sea. Okay, I just included this, and it's of course almost impossible for you to read, but it's really what you have to do if you are going to do a project development of a large floater. All the things you have to consider in terms of forces and design, redesign, etc. I hope that has enough resolution in the PDF version that you have. And some references you can go into and look more about this topic. Okay? So that's more or less the last thing I'm going to say about the physics of large floaters. Now we are going into floating cities, and this I'll go through rather quickly because it's mainly a lot of pictures, which you can look at again if you like. So we talked also the last time about motivation for building things out into the sea. So we have the problem with floods, climate change and rising sea level, and urban pressure that would like to see growth maybe in new areas, like using the sea. Industrial activities. Some of you are working on projects for chemical or processing plants on sea, so that certainly is a very important area. Harbors, floating harbors. So this is certainly an area I'm sure that will be more and more interesting in the future. Have you heard about Lake Titicaca in South America? It's a high lake. I'm not sure, it's more than 1,000 meters up in the mountains. And for hundreds of years, they have built a floating city there by straw. So this is a floating city that's been there for hundreds of years. And how do they build it? Well, you see these straws are, of course, organic material, hollow straws that is growing along the shores of that lake. So they cut the straws, and when this floating pillow is beginning to sag more into the water because it's rotting, so it's disintegrating at the old lower part, they just put more straws on top, right? So it's a very simple principle. Also, Mexico City in the first version, when it existed, when the conquistadors came there, it was mainly a city on the lake. Today, I'm not sure if this is China or it is it's Vietnam. Well, anyway, people live in houseboats and make a community. And of course, if you have a big quarrel with your neighbor, you just take your boat and find some nicer neighbors. So that is a good idea, isn't it? That shows some of the flexibility we can have by building things on sea. We can rearrange, for instance, if we have, a modular type of building, we can put these modules in a different order than we had before. So that's typically what happens when you have a houseboat and live on the sea that way. And in Japan, they have been thinking a long time about living on sea. These are smaller boats connected with kind of a pier, but they also have plans for larger cities out at sea. I guess not really realized so far, but of course in Japan they are really short of land, so that would be nice to be able to do. Flooding I mentioned, so I won't say more about that. But certainly if we had structures that could float up during flooding, that would be nice. And now we'll see a lot of pictures of ideas that people have had. And I must say, my approach is more an engineer's approach, and some of these concepts are, let's say, architects' approach, and the two are, have different ways of thinking, right? So some of these designs that you see proposed, some of them I can say right away it won't work. It's not stable. It's not practical, maybe interesting ideas, but not realistic. So sometimes the engineer has to kind of take a grip on the architect and say, this is not possible. So, and of course, nowadays there's a lot of talk about biomimicking, right? You have heard that, learning from living creatures, or learning from nature in general, how nature builds things. So I guess this is some inspiration from, what would I say, almost like a coral, isn't it? What this is, I'm not so sure. And doesn't look that pretty either, in my opinion. But again, one has to wonder, when you have these big floating structures and connected like that, how that would work together. Of course, It helps if it is in sheltered waters, but we also know that these things will move with current and wind. Probably in this case more as a rigid body motion, but still there will be enormous forces. And some of these ideas, like to dip into the water and have glass to be able to look under. Again, I would worry about the safety or something like that. Glass bottom far down underwater. And of course, if you build something that has a very deep draft, goes deep into the ocean, where would you build it? Well, you could not build it in a dry dock, could you? You have to build it floating in the sea, and starting with this thing, I don't understand how it's possible to build something like that. But interesting, right? And of course, sometimes, ideas like that inspire people to do things that also could be realistic. This, I think, is a lesson which is quite important. That was in the United States. Somebody came up with the name Freedom Ship. Of course, that triggers all Americans to like that name, I guess. So that idea came up, 1,400 meters long ship, right? Like an enormous hotel. And the first cost estimate was $6 billion, $11 billion 3 years later. And what happened was that, some people had this idea, and the idea of making a lot of money. So they got people to invest in it. A lot of money, millions and millions. And then, of course, in the end, it was realized it's not possible. This is not possible. Because the forces you get on this thing are so large that it can't be built. So now there have been criminal charges against the people who proposed this and got the financing. So that is crime of racketeering. Yeah. So it's fine to have fresh new ideas, but don't turn it into a fraud. Don't try to use that to fool people into paying money for something that's not realistic. So that's interesting. In Netherlands, of course, they have big problems with floods associated with, for instance, the Rhine, the rivers that come up, Rotterdam, and flooding. And you see what they've done here? They have houses that are built on floaters, and you see these poles. Understand what they are for? So when the water comes, the house goes up, just follows the poles. These are piled into the bottom. So here's a real building that's built on the lake. And in Netherlands, they have now some very big plans for building a new floating city. Again, as you see, in protected waters. But this is something we are going to see. And I know, for instance, in countries like India, they are seriously considering, I think particularly on the west coast, to build things floating out in the ocean. So this is something I've been working on sometime. I guess I started 3-4 years ago, 4 or 5 years ago maybe. And now you see the difference between an engineer and an architect, right? So I'm making fun of myself. So, for instance, one could build modules of, let's say, 60 by 60 meters, easily built in a dry dock, prefabricated, easy to handle, and one could, build different shapes. This is an octahedral shape, but you only need 2 different types of elements to make something like that. And it's quite interesting because if you take this structure and compare it with, this is a part of Oslo that you see in the background, the streets, right? It kind of fits with a block structure in a city. And of course, if you have these modules, put them a little bit apart from each other, then you have a floating canal, you have a canal in between. So it's kind of the same concept as a city where you have streets, but on the water you have, of course, a canal rather than a street. Or you can have also walking sidewalks if you want to. So prefabricate in a dry dock, and when it's ready to float, you fill it, or you can have several modules in the dry dock, float them out, and then do the equipment. And of course, you can have modules with different functions, etc. It can be box structure, it can be a semi-sub, and some of these things are not really here. You can have fixing or some elastic connections, or you can have hinges, and you can have some devices for when these move as rigid bodies. You can have energy absorbers, either just for the hinged motion or also for shear motion to extract energy. So in one way you do 2 things at the same time. You dampen the motion of the parts at the same time as you can extract energy. And of course, if you want to build a city on water, you would like it to be environmentally friendly, eco-city, for instance. So one could go for renewable energy. We have talked a lot about that in this course. So we can use the wave energy via the motion of the modules, sun, wind, current, heat pumps, desalination of water for drinking, recycling of water, generate energy from waste. Very little need for transport, because this is so compact that everything will be within walking distance. One can have a canal system for transport by boat, maybe electric boat, small electric vehicles that can cross canals via bridges. We can have some streets as well. One can have modules for producing food. If these boxes are partly filled with water, you can have aquaculture inside, right? And you could grow different types of clams, or have fish, or whatever. Seaweed that you like to eat here in Korea. Environmentally friendly materials. Yeah, and one can build the city gradually, add new modules, and so on. So one can see there's a lot of potential advantages by building something on the sea, right? Efficient way of constructing. And actually I did some calculations of cost and compared the cost of a floater with the cost of land in a major city. And actually the floater came out pretty well. It's not that expensive to build, let's say, a concrete box on which you can build a building. So one can have these energy absorbers, and I said they would have two functions, both to dampen the dynamic motion and to extract energy. I have to do something with some of these slides because things tend to disappear. Okay. Do you know what the Voigt-Kelvin damper is? No? You have not studied viscoelastic materials? No. Okay. I hope it's there in the PDF version. We talked about floaters for wave energy. You know, not that much energy you can extract. You can have underwater turbines of various sorts, wind turbines, and turbines underwater. Of course, I don't think one would like to build a floating city in an area where there's a lot of undercurrent, right? Probably not such a good idea. But these are things one can play with, of course. So one can put these things together. I had some students make some of these figures for me. But here you see the modular concept. You can have housing, industry, marina, food production, aquaculture, power producing units, etc., and connect them into all the functions that you expect in a city. And of course also it doesn't have to be as massive as I showed on the first slide. You just, let's say, make a crude plan, and then you can see that you can remove some elements and you can have larger canals, etc. Right? So you can make a very interesting environment for a city by some very simple modules. And it doesn't have to be this fantastic architectural design that we saw in some of the first examples. This is so much easier to build, and for people it probably makes them more feel comfortable to be in an environment that somehow looks like a city and not as being inside a clam. So some of these architect students who helped me in Trondheim made these drawings. So you see the marine environment with canals between these floating boxes. So it can look quite interesting. So it's, trying to be smart by having this modularity and so on, and all the things you can do with units that you connect together. Then last year in this course we had projects, and one group selected the project called Living at Sea, which we don't have this time, but they did some studies of modular concepts, quite interesting, different geometric shapes, how they can be connected together. One thing you will see that if you connect together many rigid bodies, the kinematics is actually getting quite complicated. Now, how should you hinge this together? It's not simple. It's an interesting mathematical problem, as a matter of fact, because you don't want to hinge things together in such a way that you constrain all forces. You want to have some freedoms so you don't get too large forces, but then again you don't want systems that kind of can collapse. They have too much freedom and things start moving apart. So one can do a lot of interesting studies with this. Different shapes, etc. And since one of the students had an architect background, you can see this was brought a step further, also to look at more organic types or shapes. So the concept consisted of different types of modules. One was a residence module, and based on underlying modules, as you see here. Again, I think, if I'm to comment on this, don't go so deep into the water. That serves no purpose. Rather make a light structure on top, and don't go so deep. And have repetitiveness of what you are going to produce. But you see this area, large area, building volume, floor space. So one can build a city like that. And these are different expressions. And again, well, something organic combined with something that's not so organic. Here's a module that is intended for energy. I think architecturally very interesting. Maybe not that realistic, but still. Look at how the wind turbines are integrated in the walls. But I think it's very fine to come up with things that are new, and they may very well not be realistic, but they can trigger some other variations of the same idea, and thereby become realistic enough to be interesting and implementable. So it was divided up in different functions, and the different units were then described. This is just a few of these examples. And forces and things like that have to be estimated, of course. Yeah. That was the end of floating cities, and with one more minute or two, I just mentioned this thing with floating aquaculture of various sorts. This is from Asia, this is from Norway, and this is becoming a big industry these days. Many of the same problems as we talked about for large floaters also apply to this kind of structures. And of course there's a big problem with fish escaping, so one has to build fences around here. One can build submerged cages, etc. So I think in the future we're going to see a lot of new concepts for fish farming and aquaculture. And this is certainly an area for innovation. But again, one has really to be concerned with safety, and particularly safety when it comes to escape of fish. So, but there are many problems with fish farming. Yeah. new concepts. I think I'll just show this to you, that this is an area in which there is many possibilities and lots of work to be done. And then, as the last little dessert, there is homework, but November 15th, right? So I give you a long time for this one. But it's an interesting homework, so that you can play with. Okay.